Hi, and welcome to EngPhys 3004 Lecture 6. This is going to be the first of 4 lectures on Chapter 14 covering internal flow. Specifically, what we're looking at is how to figure out that head loss term that we were using back in the energy equation in Chapter 12. With the stuff that we learn in this chapter, we're going to learn how to characterize the flow inside a pipe, determine whether or not it's going to be laminar or turbulent, and then from that information, estimate how much head loss we should have. This is going to let us design a piping network and then figure out which pump we're going to need to make it work without having to build it and then figure out what the energy loss was from the flow by measuring it. So this is going to potentially save us a lot of money. Okay, pipes versus ducts. A pipe is for generally transporting liquids, and because of that, the main thing that you want to do is hold high internal pressures, and so they end up being circular. A duct is for transporting gases, so the main thing that you want to do is maximize the use of limited space inside a building. Holding high internal pressures isn't so important anymore, and that means your optimal shape is going to be rectangular. This is, general, not always. There's definitely exceptions. All right, average velocity is just the average of the velocity over the cross-sectional area of the pipe or duct in flow. This is very useful because rather than integrating the velocity profile times the density with respect to area every time we want to find the mass flow rate, we can just take the average velocity, multiply by the cross-sectional area and the density to get the mass flow rate, just like we were doing back in Chapter 12. Next up, we've got some flow characterization. We've seen this before. So laminar and turbulent flow. Laminar flow is that slower, smoother flow. Turbulent is the faster, more chaotic flow. And some more numbers to this than we had originally. Laminar flow gives smooth streamlines, highly ordered, low mixing, Reynolds number less than about 2300, and viscous effects are very important. Turbulent, high velocity fluctuations, highly disordered, high mixing, Reynolds number is greater than about 4,000, and inertial effects dominate. So these Reynolds numbers that we're giving here are specifically for flow inside of a pipe, and we'll see that there's even some situations where that's not necessarily true. Depends on typical pipe roughnesses that we'd get these numbers. When we are dealing with external flow, so flow around something, the typical Reynolds numbers even are quite a lot different. Reynolds number, remember, was the ratio of inertial to viscous forces. Average velocity times diameter divided by nu is the definition for internal flow inside of a pipe. And nu, the kinematic viscosity, was equal to the dynamic viscosity divided by density. You have to pick some velocity scale and some length scale. And for internal flow, you typically take the average velocity and the diameter of the pipe. Now, if it's a non-circular pipe, you use what's called the hydraulic diameter, which is defined so that the square duct has a hydraulic diameter of just A. That's kind of convenient. And the circular tube, or circular pipe, if you want to think of it like that, has a hydraulic diameter, which is just equal to its regular diameter. The specific definition of hydraulic diameter, to make all of this work out like that, is 4 times the cross-sectional area divided by the wetted perimeter, meaning the perimeter that the fluid would actually be in contact with. So you use the internal diameter of the duct or pipe or tube or whatever, rather than the external diameter, because that's the one that matters for the fluid flow. The fluid going through a pipe doesn't have any idea about how big the outside of the pipe is, just the inside part of the pipe that it actually sees. There's some more hydraulic diameters with this calculation done. The 4 times the area, A times B, divided by the perimeter, which would be A plus B plus A plus B, so 2A plus B for this rectangular duct there. And then for a channel, you would do the same kind of calculation, but you wouldn't have the top part, so there's 1 less B in the denominator. By the way, tubes are the term for smaller, more flexible pipes typically. There's not going to be a fluid mechanics difference that we're going to be concerned with between a tube and a pipe. So if you see the term tube, that often is just a hint that the flow is slow, or the diameter is small, rather than any kind of meaningful thing in fluid mechanics that means you should treat it differently than a pipe. All right, between 2300 and 4000, the flow is what's called transitional flow. So this is the range of Reynolds number that we defined as laminar is below this, and turbulent is above that. That's not quite true either, but anyway, between those two, If you're in some kind of regime where it's not definitely laminar and not definitely turbulent, then what you find is the flow will change between laminar and turbulent somewhat randomly. This makes analyzing this kind of flow very difficult because we'll see that the frictional forces on the pipe, the head loss in each kind of flow, is very different in these two regimes. Now, part of the reason that characterizing what Reynolds number exactly is the transition from laminar to turbulent is so difficult is that it depends a lot on the wall roughness. So for typical pipes that you'll encounter, these numbers are all right. If you have something less than 2300 Reynolds number, then you should assume that it is going to be laminar. If you have something above 4000, you should assume it's turbulent. If you have extremely smooth walls and very careful control of the entrance flow like you can achieve in certain laboratory conditions, people have been able to get laminar flow in a pipe at Reynolds numbers above 100,000. Great. The critical Reynolds number is the name of the Reynolds number where the flow becomes turbulent. So for this typical case that we're taking up here, the critical Reynolds number is 4000. You can assume that that's going to be true for flow inside of a pipe unless you're told otherwise in a question. So besides the transition region being a little bit difficult for us, I think maybe I'm overselling how tough it is to tell exactly when the flow becomes turbulent. You can take it as Reynolds number above 4000 being turbulent in the same way that water above 100 degrees is going to boil. You know that if you were somehow able to control the surface conditions of the water, you might be able to get it kind of super critical if you have a really pure pot so that there's nowhere for nucleation sites to start forming for the boiling, or same kind of thing for water freezing. It can be below the temperature where it would start to crystallize if there's nowhere in particular that is preferred for crystallization. But any sort of roughness on the wall would be able to kick the whole rest of the pipe into turbulence. It's not that a particularly rough pipe would transition at, say, 2600 and a kind of smooth pipe would transition at 5000. It's more like it's around 4000 for all different kinds of pipes, except possibly super smooth ones in laboratory settings. All right, moving on. The entrance region, or hydrodynamic entrance region, is the first part of the pipe where the flow is still two-dimensional. We talked about this back at the very beginning of the course with characterizing flows, so I'll just remind you what this was about. At the start, the flow is maybe the same everywhere except right at the walls. The velocity there is the velocity of the wall, but then it's quite uniform for the rest of the area of the pipe because it just entered. Then as we move along, the walls start to interact more with the rest of the flow, and you have the boundary layer from the walls expanding and finally meeting in the center with the boundary layer from the other side. Or if this is a pipe, really this is three-dimensional. So the boundary layers from all different sections of the circular part of the pipe meet up and combine in the center. A little bit after that, there's not really the semblance of a boundary layer exactly, because the wall influence is felt throughout the entire pipe, and now we've got the situation where the flow is considered fully developed. In this region, we can calculate quite well how the flow is going to be behaving, and we're going to come up with some neat equations to deal with this. Now, the entrance length is the difference in x across this hydrodynamic entrance region. Shear stress is higher in the entrance region because there's less of a distance between the wall and where the flow is closer to this maximum amount of velocity. So with a smaller distance, there's a faster velocity gradient, kind of a faster change of velocity as you move away from the walls, and this leads to higher shear stress right near the walls in the entrance region. The highest of all right after it enters the pipe. So right at the inlet is where you have the maximum shear stress on the walls of the pipe. The entrance length depends on the type of flow and the pipe diameter. For laminar flow, you can say that the entrance length is 0.05 Reynolds number times the diameter, whereas for turbulent flow, it's a little more complicated, 1.359 times the fourth root of the Reynolds number multiplied by the diameter would be the entrance length for that. But there's a reasonable approximation that's okay for most cases, and that's just saying that in turbulent flow, the entrance length is about 10 diameters. So if the diameter were maybe 10 centimeters, then 1 meter into the pipe in turbulent flow, you would have fair confidence that the flow is now fully developed in turbulence. Shear stress on the walls is constant past the entrance region, so this makes it a lot easier to analyze the pipe if we just ignore the entrance region and say, well, that's probably not a long section of the pipe anyway, so let's assume that, let's take the total length as being fully developed the entire time, kind of ignoring the little bit of extra shear stress that we've got in the entrance region. So the friction that we calculate using this estimate is going to be an underestimate because we are not accounting for this extra friction on the walls of the pipe in the entrance region. All right, let's do some calculations now. The biggest, heaviest section of the day is 14.4 laminar flow in pipes. This is the final one of the day. We're going to give an entire lecture to the version of this for turbulence. So this is going to first derive the fully developed laminar velocity profile, and we're also going to develop how much the friction loss is in laminar flow. Here's what we're going for at the end of that, so just a preview. We're going to figure out what the velocity profile is, that it's 2 times the average velocity, 1 minus r squared over big R squared, r being the position from the center, so it's parabolic. And the max velocity is the velocity at the center, which turns out to be 2 times the average velocity across a cross-section. This is also going to let us figure out the pressure loss, 32 mu times L, so this is viscosity, length of the pipe that we're concerned with, average velocity divided by diameter squared. This particular one only works for circular pipes when we're fully developed in laminar flow, but we're going to use this to define some other terms which will be applicable more broadly. All right, here we go. Feel free to skip ahead if you're not in the mood for some derivation, or try it on your own first. The assertions we're going to make are that the velocity profile is going to be symmetric about the center, constant in the x direction, and the flow is incompressible and has uniform viscosity. Constant in the x direction is going to require the flow is fully developed, and symmetric about the center and constant in the x direction together are going to need that this is laminar flow. If it's turbulent and we don't have smooth streamlines, then this isn't going to work. Let's look at a fluid element in an annular shape here. So this is a cross-section of an annulus. Really, this goes around the center of the pipe. It is thickness dr at a radius r, has a circumference of 2 pi r then, and the volume would be 2 pi r dr times the thickness in the x direction dx. The force on this element is based on the shear stresses on the different r faces, face r and face at r plus dr, and the pressure on the different x faces at x and x plus dx. The net force, then adding that up over all the different faces, px minus px plus dx times the area of that side, 2 pi r dr, and the 2 pi r shear force times dx of the other faces, the faces on these different sides, so the inner and outer surface of the ring. They're really at a different r. We should more properly say 2 pi r plus dr for the outer part of the ring, but that's just going to lead to an r. Well, actually, I guess we do that. So this is 2 pi r tau at r plus dr. Okay, so we're good. So this subscript hasn't really been substituted in yet. We can take out the 2 pi and factor that out of every single term, so that's gone. We can also cross divide by the dr and the dx to write things in this form. Okay. Next up, what we're going to do is rewrite px minus px plus dx as just the negative change in pressure as we go from the start point to the next point, and substituting in for r and r plus dr would similarly just give us the change in this r tau from the inner part to the outer part. So let's just write that as negative d r tau on the top. Okay, so then we're left with negative r dp by dx minus d r tau by dr. rearranging and dividing by r, we get this trick that you have seen a lot in partial differential equations. We've managed to separate everything. We've got a right-hand side that depends only on r and a left-hand side that depends only on x. This is a little bit more obvious maybe after we sub in what the shear force was in terms of the velocity gradient. In fully developed flow, the velocity doesn't depend on x, so we are all good. Okay, the left-hand side has no r dependence, right-hand side has no x dependence, so both are constant. Now we can integrate each side. So we'll integrate the left-hand side and the right-hand side with respect to r, remembering that this part here, the dp by dx, must be constant with respect to r because of the separation trick that we did up here. Okay, that lets us rewrite it as r squared over 2 mu plus this constant here, adding a constant of integration from the indefinite integral. We're going to solve for that by applying boundary conditions later. Then we do this again, and we end up with u, the velocity profile, is equal to the integral of this guy, remembering that dp by dx is a constant with respect to r, and so is the constant of integration that we added. We get r squared over 4 mu dp by dx plus c1 ln of the absolute value of r plus another constant c2. The boundary conditions are that the velocity must be 0 at the wall, and the gradient of the velocity must be 0 at the center, because the velocity profile has to be symmetric about the center of the pipe, whatever shape this is. So whether it's kind of a maybe parabola or maybe a cubic function or some kind of a square root type thing, we haven't really made any assertions about that, but whatever we would get for some reasonable velocity profile, there's nothing special about the bottom versus top of the pipe, so we have a symmetric velocity profile about the center. Okay, this means when we apply the boundary conditions, we can solve for those two constants in this particular case and end up with this as our velocity profile. Great. So now that we know this velocity profile, we can rewrite it in a little bit more convenient of a form and come up with what we are ultimately looking for, the velocity profile in terms of the average velocity and the pressure loss in terms of average velocity and pipe things. So let's go back into doing that. The maximum velocity is the velocity at the center, which would, substituting in r equals 0, be this. The average velocity, we would have to integrate. By writing it in terms of the max velocity, this is maybe a little bit more convenient than this pressure gradient that we don't necessarily know at the start. So integrating after we've made that substitution, we end up with u max over 2 as the average. Neat. So in terms of the average velocity, the velocity profile is the max velocity times 1 minus r squared over big R squared, or 2 times the average velocity, 1 minus r squared over big R squared. Whether you feel like using the max velocity or average velocity, this would be the velocity profile. Average velocity is going to be more convenient for us most of the time because that one's easier to turn into the flow rate just by multiplying by the cross-sectional area. Now back to the other part of this that we were really interested in besides the velocity profile, the pressure gradient, the pressure drop per distance in x, distance along the pipe, was, from this definition in terms of the max velocity, -4 mu u max over the pipe radius, or in terms of the average velocity, -8 mu average velocity over r squared, and in terms of diameter, which is typically what we're going to talk about rather than pipe radius, the change in pressure per unit step in the x direction, unit length of pipe, is -32 mu average velocity divided by d squared. Mu is the viscosity, and let's stop and think about this for a moment. The rate of pressure loss is going to be increasing with velocity, kind of makes sense. Flow moving faster is going to be losing more pressure. It's going to require more pressure to move this fluid through the pipe more quickly. If the fluid is more viscous, then it's going to have more of a pressure drop. It's ultimately because of viscosity that we need to push through the pipe at all. Viscosity represents the friction of the fluid, and it is going to depend a lot on the pipe diameter. So really on the cross-sectional area of the pipe. For a smaller diameter, we have to apply a lot more of a pressure difference to move fluid through this pipe. Recapping. The velocity profile is 2 times the average velocity times 1 minus r squared over big R squared, pipe radius squared. And the max velocity in laminar flow is 2 times the average velocity. This is also only true for fully developed laminar flow in a circular pipe. The pressure loss was 32 length that we're talking about, average velocity divided by diameter squared. Now this is defined as the friction factor times length of the pipe divided by diameter times rho v average squared over 2, the kinematic pressure that we were dealing with back in chapter 12. So this friction factor is, its real full always applicable definition is 8 times the shear stress at the walls divided by rho average velocity squared. This is called the Darcy friction factor, and for fully developed laminar velocity in a circular pipe, it happens to be 64 divided by the Reynolds number. This tau W is really the average wall shear stress over the part of the pipe that we are talking about. And for this type of fully developed flow, it ought to be a constant along the length of the pipe. Okay. The head loss associated with this pressure loss, like before, we could get by taking the pressure difference and dividing by rho g, or in terms of the friction factor, head loss would be friction factor L divided by d, L the length of the pipe we're talking about, d its diameter, and V average squared divided by 2g. F is not going to be the same as this other friction coefficient you'll see somewhere, CF, also which a little bit confusingly is called the fanning friction factor. The fanning friction factor is related to F, but it's actually F divided by 4. For a non-circular pipe, we can still use this delta P is F L over D, rho V average squared over 2, where F had this definition in terms of the shear stress, but again, that's not going to be 64 divided by Reynolds number. Instead, you can get it from some kind of a table. So here are some results for rectangular pipes. If A over B is equal to 1, a square duct, then it would be 56.92 divided by Reynolds number. If A over B is 3, then we're at 68 divided by Reynolds number. Now, for the Reynolds number and for the D that you would use in this equation, for all of these other non-circular pipes, you have to use the hydraulic diameter that we defined earlier as the cross-sectional area multiplied by 4 divided by the wetted perimeter, the perimeter from the inside. To get the pumping power to overcome a given pressure loss, just like before, what you do is you multiply that pressure loss by the volumetric flow rate. This is going to be cubic meters per second times newtons per meter square, volumetric flow rate multiplied by pressure, and that turns out to be a watt. So this is indeed the pumping power required to overcome a certain pressure loss, or at least the energy that the pump specifically has put into overcoming that pressure loss. Horizontal fully developed laminar flow in pipes is also known as Hagen-Poiseuille flow, or sometimes just Poiseuille flow. The volumetric flow rate pressure relation for it is Poiseuille's law, which is the volumetric flow rate is delta P pi d to the 4 divided by 128 mu L. This isn't actually any new information that we couldn't have found out before. You can derive it by substituting the average velocity in terms of the pressure loss that we calculated up earlier. So we just said up here that the pressure loss was 32 mu L V average over D squared. If you were to solve this for V average in terms of the pressure loss, then you'd have pressure loss times D squared divided by 32 mu L. And that's rearranged down here. So if you take that and multiply by the area, then you can write directly the volumetric flow in terms of the pressure loss, diameter, viscosity, and length of pipe that you're talking about. All right, so recapping, the head loss that we just calculated is the frictional head loss inside of the energy equation. You still have to use the sum of the heads at the inlet and then the head added by pumps equals the sum of the heads at the outlet plus the head applied to turbines plus the head loss to friction. And in this equation, the head loss to friction, we now have some information to calculate. So this is using the friction factor L over D V average squared over 2G. One other side note is that we, in the derivation of what the head loss should be for a given length of pipe in fully developed laminar flow, we found out what the laminar velocity profile was, and that lets us calculate what alpha is so that we can use average velocity in place of the velocity in this equation, and it still is going to be reflective of the kinetic energy at the inlet and outlet. If you do those calculations, remember that it ends up being an average of velocity cubed over the inlet. You find out that for the parabolic velocity profile, you get alpha is 2. We can actually do that if you want. So let's go back up here and check out the energy equation. And back when we were deriving this, the kinetic energy correction factor alpha, I think the version that I had in the notes earlier was missing this A term on the bottom. It's all defined so that the kinetic energy calculated using the average velocity, which would be mass flow rate times alpha V average squared over 2, as long as you have the correction factor, should equal the kinetic energy actually if you were to integrate. And that would be the integral over the inlet or the outlet of V squared over 2 with respect to mass, which would be rho V dA, so with respect to mass flow rate really, and that's where the V comes from, and that's why it ends up being V cubed over 2. So we did some work up here, and this is where the A was missing. If you were to integrate this over if you integrate rho V dA, then you get V rho times V average times A, and that lets you get a V average cubed there, but also an A. So alpha is equal to the integral of V cubed with respect to A divided by the area times the V average cubed, the average velocity all cubed. Now let's try this out. Let's try out this integral. You can do this yourself if you like. So to recap here, we'll start things off with our maple, or you can use whatever integration thing you like or just do it by hand. And we'll say that the velocity is equal to 2 times the average velocity multiplied by 1 minus r over big R squared. And then we'll say that alpha is equal to, let's see if we can do this right, the integral of V cubed. Now we are doing an area integral, so we can take out the dependence on theta, on angle around the pipe, and then multiply by r from little r is equal to 0 to big R. That should do. And then we'll divide that thing by area, which is pi times big R squared multiplied by the average cubed. And we get alpha is exactly 2. All we needed to do that was the definition of alpha from earlier and what the velocity profile was.